Hi, this is Noson Yanofsky. We're doing Analysis of Algorithms, Chapter 6. Okay, it's all about Heapsort. And now, Chapter 6 and Chapter 7 is Heapsort and Quicksort. These are our first algorithms that we're really analyzing. You probably have seen, at least you've seen Quicksort before. There are different ways of sorting things. Heapsort is a pain in the neck because there's a lot of different parts of it. As opposed to Quicksort, which is really quick. Okay, but there are certain things that Heapsort has that Quicksort doesn't have, and again, we're not only learning algorithms, we're analyzing algorithms, and part of analyzing algorithms is when to use which algorithm. So that's what we're dealing with today. Okay, so first we have to start. What's a heap? Definition. A heap is an almost complete binary tree. Okay, there's more, but let me just explain to you what I mean from here. Okay, what it means is as follows. Here's a binary tree. What's a binary tree? A binary tree is a tree that has each node has 0, 1, or 2 children. Okay, a complete binary tree is where everybody has 2 children except, of course, at the leaves. In other words, it stops. Okay, so this is a complete binary tree, that's a complete binary tree, that's a complete binary tree. An almost complete, okay, means it could have more on the bottom level, okay, but all the leaves are on this side. Okay, all the leaves are on the left side. So this is an almost complete binary tree. In other words, it's complete till the second to the last level, and then it could have more, but if it does, they're all the leaves are packed to the left. Okay. Okay. Now, what's on our trees? We're not only interested in binary trees. We have each node is going to have a key. A key is something we're trying to sort. We're trying to sort different things. Okay. So what's on our tree? Okay, and we have the keys. Okay, and we're going to think of the keys as numbers, but of course you can put names, you can put whatever you're trying to sort, you can put in on your binary tree. Okay, but it has the following property. Every father, okay, a father of a node has 2 children, or no children. Every father is larger than both of its children. That is the defining property of a heap. Okay, a heap is an almost complete binary tree. So we're defining the word heap. Almost, that's kind of made up. Every father is larger. In other words, it's a bigger key than both of its children. Okay, so let's do an example of a heap. Okay, so the example is as follows. 71, that's a number. Okay, he is larger than his children. 56, 68. He is larger than his children. 12, 31, 59, 57, 6, 10, 25, 30. Okay. Okay, notice it's a heap. This is complete. There's more, but everything's packed to the left. Notice every father is larger than children. We don't make the requirement that the left child's larger than the right child, or that, look at this, here's a nephew, you know, and he's bigger. We don't care. Just every father's larger than every father is larger than both of his children. One thing to notice is if your father is larger than you, and you are larger, and his father is larger than him, etc., etc., as you go up the generations, the one thing to notice is, by definition, the largest element has to be on top. Okay? By definition, the largest element has to be on top. Okay, now, we know how to store binary trees. We know how to do data structures like that. We're not interested in that, but there's a very nice way of storing a binary tree. Okay, and the way to do it is in an array. You can store this binary tree very nicely in an array. 71, 56, 68, 12, 31, 59, 57, 6, 10, 25, 30. In other words, read it from top down, from left to right. Okay, now you might say, hey, that's just a series of numbers. This has structure to it. This has, you could tell who's the father and who's the son. So you can do the same thing here. Let me just start numbering our elements of the array. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, and so you can structure your array as follows. Here's the way to see it. If I is the father, then his two sons will be at 2 times position 2 to the I. So I is the position of the father, then his two sons will be at position 2 to the I and 2 to the I, 2 times I, 2 times I, 2 times I plus 1. Let's see if it works out. 56 is in position 2. His two children will be in position 2 times 2 is 4, and 2 times 2 plus 1 is 5. 12 and 31. 12 and 31. Okay, so it works out. 31 is in position 5. His two children will be in position 10 and 11. 25 and 30. 25 and 30. So it works out. Okay, so this is a nice way to capture it. There's another thing that you can say. Every node in position J has his father in position J over 2 floor. Okay, so let's look at it. 59 is in position 6. His father is going to be in position 6 over 2, which is 3, the floor of that. Okay, 30 is in position 11. 11 over 2 is 5.5. The floor of 5.5 is 5, and that's it. So 30's father is 31. Okay, so you can read it out. Once we have it like this, we don't have to think of it like that. We store it like this, and we don't have to think about it like that. Okay, so it's good to see it in both ways, but this is the point of having an almost complete binary tree is that by pushing all these nodes this way and having everything complete this way, this correspondence works out very well. Okay, great. Okay, so that was section 6.1. There's something I should have written here. And notice the following. Every subtree of a heap is a heap. See? Close off everything else, that's a heap. Close off everything else, that's a heap. That's a heap, that's a heap. Every single subtree, if you go down completely, it's a heap. So that's a very nice thing. Okay, but the key point is that heaps are very good, and we have a nice way of describing them. Okay, now, section 6.2. So this is section 6.2, how to keep a heap. In other words, if a heap gets messed up, in other words, you have an almost complete binary tree, but the nodes don't follow it, so how do you keep it? Okay, And the answer is, there's an algorithm. The algorithm is called Heapify. Okay, so let me write up the algorithm, and then we'll show you an example. Okay, so this is called max Heapify. The word max is because our heaps all have the largest number on the top. You can have it that another type of heap called a min heap, where the smallest, every father is smaller than his children, and that's but we're not doing that. We're going to deal with the max Heapify. Okay, it's on page 154, so you can see it in the book, and this is a variation of it. Max Heapify. You're given the array, and you're given a point where you have to start fixing the array. In other words, we can have an example. It's not going to be a Heapify. It's not going to be a heap, and you want to fix it. So what do? Okay, so let me just read it quickly so you can read my handwriting. L is equal to left of I. R is equal to right of I. If L is less than heap size of A and A of L is more than A of I, then largest is equal to L. Else largest is equal to I. We'll go through it when we deal with this, what it means. If R is less than heap size of A and A of R is greater than A of largest, then largest is equal to R. If largest is not equal to I, then swap A of I and A of largest, and then recursively call itself max Heapify A comma largest. Okay, I'll explain to you what it is in a second, but I'm going to explain to you, but here's an example. Notice this is an almost complete binary tree. All the children are to the left on the bottom, but it's not a heap. 5 is the father, 91 is the child, 59 is a child. That's not a heap. That doesn't satisfy the heap property. This does satisfy the heap property. This does not satisfy the heap property. 16 is above 12. This is okay. This is not okay. Okay, so this is okay. Okay, so we have to do it. Okay, so here's the way max Heapify works. What it does is, it looks at a father, which is I. It looks at its left child and its right child, and it finds the maximum of those three. Okay, so you have to find the maximum of 3 elements. How do you find the maximum of 3 elements? Well, what you do is you compare 2 of them, and whatever is the largest of those 2, you compare to this one. Okay, so that's how you do it. Just how do you add 3 numbers? You do 2 at a time. Okay, same thing here. When you have 3 things you want to compare, you compare 2 of them, and then you take the largest of the 2 of them and you compare it to the third one. So we're going to compare the element at position I, the father, the element at position L, and the element at position R. So if L is less than heap size, you'll understand what this is about later, okay? And A of L is larger than A of I. If the left child is larger than the father, then the largest is the left child. Else, if he's not larger, if A of L is not, if the left son is not larger than the father, then the largest is equal to the father. So far. Okay, this just compares the left and the father. Now, if R is less than heap size, otherwise we don't do this comparison, but again, we'll explain this later, and A of R is less than the largest, now that you have the largest of the father and the left, now you compare it with the right. If the right child is more than the largest, then the largest is equal to right. Fine. Okay. Now, question, when do you have to do any changes in your tree? And the answer is you have to do the changes if the largest is not equal to the father. In other words, if one of the children are larger, then you have to do it. So if the largest is not equal to the father, then you have to do this change. What change do you have to do? Swap the largest and the father. Bring the largest child, which is the largest of all 3, bring it to the top, make the father into one of the children. Okay? But the main point is, this is a recursive algorithm, and once you changed, then you call the algorithm to itself. You call the algorithm itself the same A array, but now instead of calling it the father, you call it the largest one. And what this does is it trickles down, goes down further and further through the tree. Okay, so let's work through it. Let's see how this works. Okay, we have a different color pen. So let's say I call the max Heapify at the top of the array. You don't have to. You can call it here and try to fix this up. By the way, it won't do anything here because this is a nice heap. It will do here. Okay, but let's try it here. Okay, 5. I'm going to compare it to its left child, 5 and 91, which is larger. Answer 91. Okay, and then we look at, so 91. What's larger, 91 or 59? Answer 91. So he's the largest. So what we do is we swap this guy and this guy. 91 goes up here, 5 goes over there. Okay, so far so good. Okay, next, now we call max Heapify again, and we compare these 3 elements, the father and the 2 children. We swapped him with this, and now we have to trickle down and go down. So what's larger, 5 or 12? Answer 12. What's larger, 12 or 31? Answer 31. So he's larger. So what's going to happen is we're going to swap the 5 and the 31. 31 goes up. It's going to be larger than 12. And so 5 goes down. Great. And now we continually trickling down. What's larger, 5 and 25 or 5 and 30? Anyways, 5 and 25. 25 is larger. 5 and 30, 30 is larger, so we swap again. So this becomes 30, and 5 trickles down all the way to the bottom. Okay? Now, this is not a heap. This whole thing is not a heap, but this branch is a heap. And we're going to use this max Heapify in a lot of different ways, whatever, to make heaps and to fix heaps. Okay, this is not a heap either. This is not a heap. But what it touched, it fixed. Okay, great. Okay, so this is a nice algorithm. Question is, how much work does this algorithm do? Okay, let me just say what this max Heapify, this heap size does. Okay, we're going to keep track of how large the heap is. So let's say I tried to do this. I tried to fix max Heapify from here. Well, he is in position 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and his 2 children are what? His 2 children are in 9 times 2 is 18 and 19. Well, 18 and the heap, there is no 18 and 19. Okay, there is no children at 18 and 19, and so we don't even do this comparison because if you don't have children, this by itself is a heap, and so we leave it alone. Okay, so we have, besides A, we have to keep track of how many elements are in A, and that's called the heap size. Okay, question. How much work is done when you call Heapify? Okay, and let me give you the intuition first. What's the worst possible thing that can happen? The worst possible thing that can happen is you can start all the way on top. You can start all the way on top and trickle down all the way to the bottom. Okay? Now, how tall is a binary tree? We said that that's about log of n. A binary tree is about log of n. So the worst thing that can happen is you can call itself within the algorithm. There's only 2 comparisons. That's not an important thing. But the question is, how many times do you call itself? And the answer is the worst that can happen is you start at the top of the tree, you go all the way to the bottom of the tree. In other words, you don't stop anywhere and say, "Oh, that's it, no more. Don't have to go further." That was the father is the largest. You don't have to stop. The worst that can happen is you have to start at the top of the tree, go all the way down to the bottom. Okay, and the tree is log of n long. Okay, but I'd like to show it to you a little bit more formally because it's kind of interesting. Okay, if you have a complete binary tree, okay, then you can check this out yourself. The number of nodes on the bottom is equal to the number of nodes all the rest is almost equal to, or it's one more than all the rest of it. Okay, you can see this with a regular binary tree. Ready? There's the 4 nodes on the bottom, 1, 2, 3 nodes on top of that. Do another thing. There's 8 nodes on the bottom. There's 1, 2, 3, 4, 5, 6, 7 nodes on the top. Okay? If you did another one, there would be 16 nodes on the bottom, and there would be 15 nodes altogether. So this is called exponential growth, okay? And the point is, all the nodes that you can have, the last generation is equal to one more than all the previous generations. And they say about human beings, there are 8 billion people on Earth now. That's a lot of people. It's more people than ever existed, combined, something like that. Okay, now, we don't have a complete binary tree. We have an almost complete binary tree. Okay, so if you look at the way the number of nodes are split up, okay, this is going to be n over 3, this is going to be n over 3, and this is going to be n over 3. Okay, you can see this here. This is about. So the number of nodes on the bottom is equal to the sum of all these. But you also have this. So, conclusion. If you start off with n nodes, okay, what's the worst possible thing that Heapify can do? What's the most possible work that Heapify can do? And the answer is, the worst that can happen, by the way, I can Heapify from here, and then trickle down here, and then trickle down here, and you know what? This father can be larger than both of his children, and we stop right there. That's a good thing. Okay? Another thing I can do is I can start Heapifying here, and see that this father is larger than this child and this child, and you stop right there. You did one comparison, two comparisons, you're finished. Okay? So that's the best case scenario, but we're not interested in the best case scenario. We're interested in the worst case scenario. The worst case scenario is you start all the way on top, and which way is worse, this way or this way? Okay, which way is worse? Well, if you want to trickle all the way down, this way is worse. Okay, so you'll trickle all the way down, doing Heapify the whole way until you get to the bottom. Okay, so how much work was done? Well, basically it's as follows. It says, if you have n nodes, okay, you do one or two comparisons, we'll write this as one, and then what you have to do is 2n over 3 nodes left. So you do one comparison, you get here, not here, and then look how many nodes you have in this subtree. 2n over 3, 2n over 3. So with one comparison, you can knock out 1/3 of it, and you can do 2/3 of this. Great. Now let's do the master theorem. We do the master theorem every day the rest of the class. Okay, A is equal to 1, B is equal to not 2 over 3, but 3 over 2. Okay, and you do the master theorem, and you look at log base 3 over 2 of 1. What do you have to raise 3 over 2 to in order to get 1? And the answer is 0. So you're talking about functions n to the 0, and that 1, f of n is equal to 1. Okay, that's equal. So it turns out it's the max, it's the middle case of the master theorem. Okay, and so t of n is equal to n to the 0, or 1, times log of n. Okay, which is equal to log of n. Okay, boom. Notice, if you did this with a tree, you'd get how tall is this tree? It's about a log of n, but log of 3 over 2, it's not really log of n because you can go further down. So anyways, but it's up to a constant, it's log of n. Okay, so that's how much work is done. So we gave the intuition, but then we formally did it with the master theorem. Make sure you know the master theorem. Okay, great. So we know how much work is done with that. Okay, and we're up to section 6.3. The question is, how do you build a heap? How do you build a heap? In other words, you're given a bunch of numbers. You're given a bunch of numbers in an array, and you want to make a heap out of it. Okay, so consider the following. Okay, this is section 6.3. You're given a bunch of numbers, 16, 3, 6, that's an 18, and that's a 9. You're given a bunch of numbers, and you want to make a heap out of it. That's an 18. Okay, how to do that? So this is an almost complete binary tree, but it's clearly not a heap. Now I know how to make it from one place. I use Heapify to make it from one place down. But how do you make the entire thing a heap? Okay? And we're going to need a heap to do the heap sort. And the answer is as follows. Look, this, just look at the 9 itself, that's a heap. That's a heap. That's a heap. That's not a heap. 3 with the father is 9. So what I'm going to do is I'm going to go through the heap backwards from here halfway through on. Okay, so how am I going to do it? I'm going to just go here, I'm going to Heapify here, I'm going to Heapify here, and then I'm going to Heapify there. So let's do this. 3, let's 3, 9, so this says that the father is larger, so I'm going to use Heapify. I'm going to make this a 9 and this a 3. Okay, then I'm going to go back here. 16, 6, what's larger? 16. 16 and 18, what's larger? 18. So I'm going to make this an 18, and I'm going to make this a 16. Okay, now I go back one up. Okay, here's the thing. This changes as we go along, and now I'm going to go up one more. Okay, 5 and 18, what's larger? 18. 18 and 19, what's larger? 18. So now this becomes 18. This becomes 5, and Heapify calls itself. So we're going to do this again. 5 and 6, what's larger? 6. 6 and 16, what's larger? 16. So we swap this. This becomes 16 again. Isn't that interesting? And 5. This goes there. Now that whole thing is a heap. Okay. So what we do is we go the bottom half of the n elements are already heaps, because they're leaves. What we do is for I equals n over 2 down to 1. And what we do is we call Heapify of a comma I. That's it. At the end, you got a heap. What does this look like in terms of a matrix? This is 18, 16, 9, 6, 5, 3. Okay, that's very good. Again, the first element is always the maximum of all of that. So that's the beginning. That's going to be the largest. But this is definitely not ordered. Well, it's in reverse order actually. But that's fine. Okay. Question, how much work is done? How much work does it cost to get an almost complete binary tree into a heap? And the answer is, well, I had to do this loop n over 2 times, and each time I call Heapify. How much work does Heapify do? Okay, we did that 2 minutes ago, and Heapify does log of n. Okay, so this is a member of theta of n log n. Okay, not hard. Great, so now we know how to make a heap. Yeah. Question, what does that have to do with heap sort? Okay, what does that have to do with heap sort? So now we do the heap sort. Okay, so let's just recap. Section 6.1 told you what a heap is. 6.2 told you how to fix a heap, called Heapify. 6.3 told you how to make a heap using Heapify. And now we do section 6.4, which is called Heapsort. Okay, and this is the actual algorithm. Okay, I'm going to write the algorithm and then we'll go through a nice example. So it's basically as follows. Heapsort accepts an array. Okay. First thing it does is build heap of A. In other words, the array is just an array. I want you to make it into a heap. And how do you do that? You forget about the leaves, because the leaves are okay. You go from halfway up to 1 and you build the heap using Heapify. Then you do the following. For I equal 1, length of A down to 2. Okay. Exchange. The book sometimes says exchange, sometimes swap. A of 1 with A of I. Explain to you in a second. You'll see this. Okay. Heap size equals heap size minus 1. Heapify A, comma 1. That's it. Okay, so let's do an example. The example is hard to take notes. This is page 160, so you can read it online. It's hard to take notes to do this because you're going to see I'm going to erase things and change things a lot. I'm going to do it with the eraser, but in the book there's a nice example where they do it step by step with a lot of little trees, and you'll see how it works. Okay, and the idea is as follows. Take this. Here's a nice heap. 18, 16, 9, 6, 5, whoops, 3. Okay? Okay. Now I'm going to write this as a matrix, as an array. So this is 18, 16, 9, 6, 5, 3. Okay? And the heap size is, this is heap size, 1, 2, 3, 4, 5, 6. There's 6 things in the heap. Okay, so let's see what we do. Okay, first thing we do, we want to get it in ascending order. We want to sort this in ascending order. That means the numbers go up. Okay, what is the largest number on the heap? It's always the top. Okay, well I'm going to leave this out. What's the highest number? It's always the top. So I want to put the top, which is the highest number, at the end. Okay, so basically what I do is take this 3 off, and I say this is the top. Okay, okay, good. We're going to use, pop it off, and put it someplace. Okay, great. Now what should I put instead of there? Okay, I can't just take one of its children because I don't know, because it doesn't work. You know, so what I do is, it doesn't work because nephews might be smaller. It doesn't matter why it doesn't work. What you do is you take the 3, the smallest, not the smallest element, the rightmost element on the bottom, and you change it. Okay. So what happened here was there was a 3 over here. I bring the 3 up to the top. There was an 18 here, and I changed positions. Okay, but now, so now I bring the 3 to the top. Okay, the 18 is over here. It's not on in your heap anymore. It's over here, but it's not in your heap. Your heap size is now 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now Heapify. Okay, so we exchanged the first thing, the highest thing, with the ith thing. Okay, and now we reduce the heap size. The heap size was 6. I put this back. Now it's 5, and now Heapify. This is not a heap. This is no longer a heap. Make it a heap. How do you make it a heap? This swaps. You get 3 and 16. Okay, this swaps, this becomes 3, this becomes 6. Okay? Okay, great. Now, again, I just heapified. This is a heap, 16, 6, 9, 3, 5. And now I'm going to write it as a heap, 16, 6, 9, 3, and 5. And now we do part 2. Ready? What's part 2? We go next one. What's the next one? Here's length of A down to 2, so we're up to here now. Okay, and what I'm going to do is I'm going to swap this guy and this guy, which is going to correspond to swapping this guy and this guy. Okay, so let's do that. What we get is 5, 6, 9, 3, 16. Then Heapify is equal to Heapify, oh, don't forget the 18, it's still there. Heapify is equal to Heapify minus 1. You get like that. That's new Heapify. And now we have that. Okay? Good. Let's write this as a almost binary tree, which is not a heap. This is not a heap anymore. So it's 5, 6, 9. He has a child 3. Okay? Now your heap has only 4 elements. Heapify, what's larger, 5 or 6, 5 or 9? We're up to Heapify from the top, 5 or 6, 5 or 9. So this becomes 5, this becomes 9. We're finished heapifying, okay? And now, we have to swap. Now what happens is, okay, so now this is 9, 6, 5, 3. Okay, let's put it without the crossing out. Again, it's hard to see, but 9, okay? And now we're dealing with this. Okay? Now again, top of the heap is always the largest element. We're up to the 3rd time we're doing this. So basically what I'm going to do is I'm going to swap the top of the heap with the bottom of the heap. That corresponds to swapping the top of the heap with the bottom of the heap, or where we're up to in the heap. Okay, and we do it. So basically, the 3 and the 9 swap. Let's do it. The 3 and the 9 swap. The 3 goes to the top, the 9 goes to the bottom. We heapify minus 1. Heapify minus 1, now this, etc. Okay, and now we do it again. Okay, so we have 3, 6, 5. Okay, that's not a heap, we call heapify. This becomes a 3, this becomes a 6. We have 6, 3, 5. So this becomes 6, 3, 5. Okay, pull off the 6. Okay, and eventually, I'm not going to do any more. Pull off the 6, you get 6 over here. It's going to be 3, 5, 6. Okay, I forget what that was. And that's a 9. Okay. Okay, great. And that's the end. The heap size is now 0. There's nothing in your heap anymore, but you have an ordered array. That's exactly what it does. Okay, great. So let's just recap. Basically, it's as follows. In a heap, the top element is always the largest element. So pick off the top element. Put it at the end of the array. Now, you can't just leave the top element empty, so you go find something on the bottom and you put it on top. You find the last element, you put it on top, because your heap, when you pulled off the top element, your heap is messed up. So you want to fix it up. So you put something on top and you let that thing trickle to its correct position. That's what you do. You let that thing trickle into its correct position. Okay, it trickles down, etc., etc. And you keep on doing this over and over. Question, how many times do you have to do this? And the answer is, well, every time you pull off an element, you put it at the end of the array. How many elements do you have altogether? Answer, 9. N. You have n elements altogether. So you're going to have to do this procedure n times. Okay, we did it 6 times here. Okay? Okay, and how much work is done each time you pull it off? Well, the only thing that's done here, you're doing this n times, n minus 1 or something like that. The only thing that's done is heapify. That's it. exchange, Heapify. So how much work is that? Log of n. That's the entire thing. Okay, so let's go through this. This is the Heapsort algorithm. Build heap, that's n log n. Okay, and then you do this loop n times. Each time in the loop, the only thing that you're doing is log of n of it. And so you get basically, this is 2n twice n log n to make the heap, and n log n to pull it off. So that's that. Okay, now Heapsort is a pain in the neck. Just think about how much steps we had. We had to make Heapify, we had to make the heap, and then we had to pull off things from the heap one at a time. It's a pain in the neck. But it works n log n. 2 times n log n, but that's still, it's n log n. Okay? And n log n is pretty good. Now, it's n log n in the best case, it's n log n in the worst case, it's n log n in the average case, because you're always doing all these operations. Okay? You're always doing these operations, so it's not so terrible. Okay, so it's n log n. Okay, people don't like Heapsort because it's a pain in the neck, because there's a lot of little steps to worry about, but that's okay. Let me just tell you a positive thing that people do like Heapsort, and the reason why they like it. Okay, the positive reason is the next section, section 6.5. It's called priority queue. Okay, so the reason why people do like Heapsort is because this concept of a heap shows up all over, and you can use this stuff in different areas. So not only can you use it in sorting, but you can use it in different areas. Think of a Xerox machine. There's a lot of little jobs that a Xerox machine does. Okay, and it has to do these different jobs. Okay, now there might be a lot of computers connected to a Xerox machine telling it what to do, or a printer. Let's think about a printer. And the question is which job to do first. What the computer does is it maintains a queue, a priority queue, with the most important job up on top. Okay, and so when the printer's free, what it does is it grabs the top job with the most important. Maybe the president of the college sent that job, or the chairman of the department, or the lowly professor, whatever. But that job has the priority, pulls it off the queue, does the job. Now, it maintains the queue. You have to maintain a priority queue. And how do you maintain the priority queue? You pull the thing from the bottom of the queue, okay, and you put it on top and let it trickle down to its correct position, and then you have it. Okay? Okay, so priority queues are a thing that are used with Heapsort. Okay, Heapsort is a lot of fun. You should read section 6.5 because there's a lot of interesting things there.